Hello, I'm Alysson Muotri, Director of the UC San Diego Stem Cell Program, and this is the Sanford Stem Cell Clinical Center. The Sanford Stem Cell Clinical Center is one part of the UC San Diego CERM Alpha Stem Cell Clinic. The CERM-funded Alpha Stem Cell Clinics are a network of top California medical centers like the UC San Diego Health that specialize in bringing the latest stem cell clinical trials to patients to treat many afflictions, among them blood disorders like leukemia. I sat with Catriona Jamieson, who heads the UC San Diego CERM Alpha Stem Cell Clinic, and share insights into what the present and the future of stem cell therapies are and how the alpha clinics are making that happen. What are the most exciting things that's coming out from this field?
I think what's really exciting now are things that took 20 years to get to the clinic, like stem cell gene therapy for severe combined immunodeficiency. Now we say, of course you can do that, and within the Alpha Clinic network. So the Alpha Clinics were called alphas in the first letter of the Greek alphabet because they're the first. It was a grandiose suggestion that we should have one-stop shopping for patients who have degenerative diseases that could benefit from stem cell therapies. And so it has expanded where we were one of the first 3 sites to include not just UCLA and UC Irvine, not just UC San Diego and City of Hope, but UCSF, UC Davis. You know, we're a catchment area of 20 million people, and we're trying to bring stem cell therapies closer to home. So the most exciting thing to me is that we can do that as a network, that we can share clinical trial protocols, we can share confidentiality agreements and contracting. That may not sound very exciting to people that are saying, but what about the science? This makes the science possible in the clinic faster. So it means we can get up and running very quickly. And when you think about technologies that are curative, like stem cell transplants for severe combined immunodeficiency, which they are, making these kind of really involved therapies more accessible to patients is our whole raison d'etre. So whether it's for chronic granulomatous disease or Stephanie Cherky's work with inborn errors of metabolism, I think we can do that for these rare diseases. But I think what that tells us is we can do that for more common diseases. And we can really start making inroads on spinal cord injury, type 1 diabetes. Those are the trials we're doing. So when we started our trials, we did a phase 1 trial, first in human, to target leukemia stem cells and chronic lymphocytic leukemia with an antibody we made with CERM funding. So we called it CERM-tuzumab. So we started that September 2014. We started a spinal cord injury trial with neural stem cells. September 2014, and we started a type 1 diabetes stem cell trial also September 2014. We thought everybody did that first in human, you know, 3 trials in 1 month. And so we just thought it was possible, and it's, you know, that's what's really exciting, that you can get those technologies. In terms of hematopoietic stem cell changes, we've talked about CRISPR. So, you know, a number of our labs have worked on trying to edit DNA, and I think what's really exciting, as you know, is I'm very excited about editing or repairing RNA. So DNA you can change or try and correct when the cell is dividing, but a lot of the changes happen in cells that aren't dividing, and they've changed their RNA more than their DNA. So what I mean by that is if you try and remodel your house like we're trying to do now, the DNA is like the architect's blueprints. The RNA is the engineer's interpretation of that blueprint, because often when you look at the architect's blueprint, it's completely different. The engineer said, no, there has to be a retaining wall, there has to be something to hold up that building. And then the protein is like the builder. So you have these 3 levels. And what happens in a lot of blood-related diseases is you have problems at all 3 levels: DNA, RNA, and protein. And what we found in various blood cancers is you activate an enzyme that really affects the RNA called ADAR, ADAR1, so ADAR is on our radar. But more than that, people have been very, very clever to say, there's an RNA editing enzyme that went awry in cancer. Let's see if we can make it behave as an RNA repair mechanism in cells that are no longer dividing, post-mitotic cells. So I think that's extremely exciting. And that's a basic stem cell technique. It's by understanding stem cells and how they clone themselves or self-renew that we started looking into things that can be repair strategies. So sometimes by investing in technology, you see something completely different than anything you'd ever thought you could use in an advantageous way. So I think that's really what's happened now that we're racing into clinic. There are things that we can do that are even more clever because of this sense of a collective responsibility for getting stem cell therapies to the clinic.
And you guys are putting yourselves on the spot, right? I mean, by doing that.
Thanks for putting that out. Yes.
But is it a hope that other parts in US, perhaps in the world, will actually reproduce that model?
You know, that is certainly my hope, and it's certainly my entire drive to say I hope that this can be reproduced in other places. There's something unique to this environment that's hard to transplant into other places, and it's not because they can't, it's because they don't think they can. And so giving that sense of ridiculous enthusiasm that we have, and the sort of casual thing where we can have these discussions and say, what do you think? Is this a crazy idea? And then you'll say, yes, it's a crazy idea, but I have this reagent that you can use. So you can test it. So we'll have these discussions and they seem casual, but that's how you get really important scientific ideas to the clinic. That's what abbreviates the timeline. So if you talk to people, they say, oh, it takes 15 years to translate discoveries to the clinic. That's because it's like, did you watch the Super Bowl? Yeah. So imagine if you changed the quarterback at halftime.
Right. Yeah.
And then imagine if you changed the stadium as well. You would really mess up the game. And that's what happens in therapeutic development all the time. They change the team, they change the whole goal, and so people lose track of what was going on and they drop the ball. By having integrated teams where we have the Sanford Consortium for Regenerative Medicine, we make basic science discoveries here, we have sufficient funding to be able to translate those discoveries, de-risk those discoveries by doing a lot of the initial translational work ourselves, which usually is thrown to a team that doesn't know anything about it in industry, and then get it to the clinic for the phase 1 with interaction with the original team, the original investigators. Then we don't drop the ball and not know what was going on in the lab. Because it's still very scientific in the clinic when we get into a phase 1 trial. Usually you can look at safety and tolerability, but not proof of concept. We still have to show that the mechanism is relevant for that disease. And so by maintaining that continuity of communication, we're able to make sure that we stay focused and that we don't spend a lot of time spinning our wheels when really we could have done a better designed clinical trial. We're at a phase right now when you look at stem cell research in terms of the basic, the translational, and the clinical aspects where we're going to do reverse translation, where we're going to understand from looking at people in the clinic where we didn't quite get it right and say, wait a minute, we've got to make something better for you.
That's a good point.
So it's going to be more bespoke. Let's make this more precise and let's see what can we do for you that is very specific to your disease, where it may be a different variant of a Cardiac-Gutierrez syndrome or whatever it is, but something where we can combine genomics with stem cell research, so we do precision regenerative medicine, and we can do that in a continuous way. So when I see people in clinic, they say, oh, you've dealt with my bone marrow disorder, but I've got this terrible disc disease. Can you help to repair my degenerative disc disease? And so, aha! So we can work on one-stop shopping. So not only the actual specific disease that people came to us for, but what else is going on in your life, your overall health, so we can start to improve these other aspects because they all act on each other.
Thanks so much, Kat. I think this was very insightful, and I hope we can do this one more time again in the future.
I hope at least once, Alysson.
Yeah.